Right. So, hi, grade 12. Hi, it's Mr. Stone here, speaking from the ether, from the Ethernet, the internets, the interwebs. Good to see you. Oh, I don't know if you can. I can't see you, but you guys can see me. Nice to talk to you. Look there. There's the camera. All right, looking at this camera. Hi. How's it going? Okay, so I hope you're all well. Hope everything's going okay in this interesting times. Um, just if you guys have time, don't be stressed too much about things. But if you have time, you know, I'm going to go through all our lessons and go through all the problems and post them all on the website, and you guys can do what you need to do. Okay, so don't get too stressed about this, but this is just to help you guys out as we go along. I'm going to go through all the lessons. I'm going to pretend that this is like this is our room 229, but it's room 229 online. It says up there. So we were talking about conservation of momentum, right? When in any sort of collision, the momentum before and the momentum after have to be the same. These fundamental rules of physics, universe, right? So the next thing we need to go talk about is how the collisions can either be elastic or inelastic. What that means. What's the definition of elastic? We talked about elastic potential energy before, but let's go a little bit more in depth here. So let's say we have two balls and they're going to collide. We have a ball A that has initial velocity VAI, and another ball B has a velocity VBI. When they collide, we know their momentum is going to be conserved. And so we can come up with a conservation expression. But what about its energy? We learned from grade 11 that we can calculate kinetic energy as half mv squared. That's what this is. So this here is the kinetic energy of ball A. And this is the kinetic energy here of ball B, right? They have this initial kinetic energy, and then they're going to collide. When they collide, all that energy is gone, right? Because they stopped. Right? They've stopped moving, so they have no velocity. So if they're stopped, they have no more kinetic energy. But we know from the first law of thermodynamics that kinetic energy cannot just vanish. It has to go somewhere. It has to be converted into some other energy. In this case, all the atoms in the thing have to deform. So our two balls, they smush into each other. And when they smush into each other, they store their kinetic energy in some sort of elastic potential energy, and then they release it and they head back the other way. So we can have these expressions here for the final kinetic energy. Now, the definition of an elastic collision then is that if all the energy we started out with, the kinetic energy that we started out with, is conserved after the collision. So all that energy that was stored in the material then released again. Now we know from the second law of thermodynamics that that's impossible. So there is no such thing as a perfectly elastic collision, but we can see some of them, right? And you know that there's no such thing as a perfectly elastic collision. A perfectly elastic collision would be like if I take a bouncing ball and I drop it, it bounces right back to the same height. And it kept going forever and ever. We know that's impossible. Bouncing balls essentially slow down. Even though this super mega ultra mega bouncy ball, if I just drop it, I'm not throwing it down. If you throw it down, it has extra kinetic energy that it's able to go to a higher energy. But if I just drop it, it'll never bounce back to the original height. So some of the energy is lost. So all collisions are inelastic, but some are more so. If two cars collide and they smush into each other, they become one thing. That's a perfectly inelastic collision. Those crumple zones. That's why cars have crumple zones. That when two cars collide, their energy, that kinetic energy, is absorbed. So the two cars collide, that crumple zone, the thing crunches it all up together, and instead of the energy being transferred into you, having to change your motion, it slows down the car gradually. Instead of the old cars when they first you collided, then the person would have to stop instantaneously, and it caused all kinds of traumatic injuries. We have crumple zones now. So when the cars collide, they have this inelastic part where they deform inelastically. And that's what we call, like if you take a spring, for example, and you stretch it and it goes back to its original place, we call that an elastic deformation. If I stretch it too far and it doesn't go back to its original size, that's an inelastic. Okay, so let's do an example here. So let's say I have a golf ball. It's, what's that? That's 52 grams. And it's traveling east with a velocity of 2.1 meters a second. Collides with a billiard ball of 160 grams. Okay. The golf ball rolls backwards with a velocity of 1.4 meters a second. Was the collision elastic? So really, what they're asking you is that they're asking, so is the kinetic energy with to the energy afterward, right? That's the question. But we need to figure that out. Now let's make our lives easier. We're gonna, instead of calling it EK, from now on, whenever I write, whenever I write just big K, that's the kinetic energy. Okay, so the kinetic energy to begin with, is that equal to the kinetic energy afterward? Okay, so I'm gonna try to move this back a little bit here. It doesn't wiggle while I write on it. Okay, so how are we gonna do this? So let's start off with this as being a momentum problem, right? This is really just a momentum problem. So let's say we know that momentum is going to be conserved. We're not necessarily sure about energy. So let's go with the first assumption that momentum is conserved. So we know that the momentum to begin with is going to be equal to the momentum afterwards. So these are vector expressions, right? So that's our big idea in this unit about conservation momentum. That this expression tells us that the momentum to begin with, the momentum of the billiard ball before, or the golf ball, sorry, is equal to the combined momentum of the two balls afterwards. So to begin with, there's only the golf ball, so we can say that it's the mass of the golf ball multiplied by the velocity of the golf ball to begin with. I'm gonna, because this is a one-dimensional system, I go back here, this is in one dimension. Let's get rid of the vector sign. So that's going to be the mass of the golf ball. Oops, sorry. That's going to be the mass of my golf ball, velocity of my golf ball afterwards, plus mass of the billiard ball, velocity of the billiard ball afterwards. I know that if momentum is conserved, these two things have to be the same. Isolating for what I want. What do I want here? I want to know, I know the initial velocity of the golf ball. I know the final velocity of the golf ball. I don't know the final velocity of the billiard ball. Right, so if I wanted to know the velocity of the billiard ball afterwards. So isolating for that, the velocity of my billiard ball at the end is going to be equal to the golf ball and the difference in their velocities, right? The rate of change, the amount of the change in the velocity. So that's the initial velocity of the golf ball, take away the velocity of the golf ball afterwards, all over the mass of the billiard. Okay. Right, and if I work that all out, I get a 1.02 meters per second. Right? How about actually let's just put all the numbers in. It's a little bit, got to be a bit more careful here. So the ratio is going to be 0.0520. That's the mass of the golf ball. Billiard ball is 0.60. And excuse me for being a bit messy. This is tricky like this. So it's 2.1 meters. Take a meter per second. Take away. This is the tricky bit. Remember that the golf ball afterwards bounced back at a speed of 1.04, right? So that's going to be in the, oopsies, that's going to be in the negative direction, right? So then we have subtracting a negative, it's adding, and everything all works out to 1.02 meters per second. Okay, so this is my velocity of the billiard ball after the collision. Okay, so I've got that. I have an expression for, I know, sorry, not expression. I have a solution here for the velocity of the golf ball. So let's go to energy now. So we've used momentum. We know it's going to be conserved, so we use that first as our, to get all the things we need to know. So let's consider now, what is the kinetic energy to begin with? That's going to be, the only thing that was moving there was the golf ball. So it's going to be 1/2 mass of the golf ball, velocity of the golf ball to begin with, squared. That's going to be 1/2 0.0520 kilograms divided by 2.10 meters per second squared. What's that going to be? That's going to be 0.11466. What are the units on that? Energy. What are the units? Units of energy are joules. Okay, so that's my initial energy. Let's now go and do the same thing for afterwards. My kinetic energy after the collision happens, which is going to be 1/2 the mass of the golf ball, velocity of the golf ball afterwards, plus 1/2 the mass of the billiards ball, velocity of the billiards ball afterwards. That's why we did that thing with the momentum. We needed to calculate what this velocity of the golf ball was. We didn't know this one yet. We knew all the other velocities. We didn't know this one. We had to work that one. So when I work this out, I end up with, you guys can do the math here, but it's 0.1115, 1135 joules. Okay. Now, what have we noticed? Is the energy conserved? Is the kinetic energy to begin with equal to the energy afterwards? No, they're not the same. So therefore, this is an elastic. Sorry, is it an elastic collision? Is it an elastic collision? Elastic would mean that all the energy is conserved. It's not. So this is an inelastic collision. Okay? So it's an inelastic collision. That's because the two energies before and the energy afterwards are not the same. Now, try one of these famous problems, the ballistic pendulum. How can we use a pendulum here, basically a sort of wooden contraption that has a bunch of clay in it, attached to these two strings. I'm going to shoot a bullet at it. Okay, this is a way that you can calculate the speed of a bullet. So the bullet is going to collide with the hunk of clay, inelastically collide with it. So all the energy will be stored in the material, and all that energy is then going to push the pendulum over, and it's going to rise up to some height here. So it starts off with 0 height, and then it's going to raise up to some height. And if we are looking at this from a practical point of view, measuring that height is going to be difficult. The angle, which is over here, will be a lot easier. Not showing me my cursor. All right, sorry, but oh, there it is. The angle here will be a lot easier. You just put a little metal stick here, and as the string pushes it, it just locks to the maximum extent. We calculate the angle. So we need to come up with a simple way of coming up with the velocity as an expression of the angle here, and it comes up to this funky looking expression here. So we have to derive this. Oh, derivations. We love to derive equations in this class, don't we? Well, this one does. Okay, so this is the velocity expression in terms of a constant gravity, the length of my string, the angle that I measure, and here the ratio of masses, the bullet mass to the ballistic pendulum mass, ignoring this. Okay, so let's think about how we can do this. So we know that this is going to be again a momentum problem and an energy problem. So let's think about the momentum that we look at. So I know that I'm going to have, again, the initial momentum is going to be equal to the final momentum. Okay, we're just going to get rid of vectors right now because we know that we're gonna imagine the whole system in one dimension. We're not looking at the swing. We're gonna have two parts. So think of it like this. There's two things happening. The one thing happens is there's a collision between the bullet and the thing. So I have my block here, and I have a bullet that hits it. Initially, the block isn't moving, and the bullet is moving. Then there's going to be a collision, and the whole thing will start moving. We're going to ignore that part here. That's going to be our second half. We're going to find out what is the velocity of that whole collection, bullet and block, together right after they collide. Once we get that velocity, we can get an energy, and from that energy, we can get a potential energy as it rises up. Okay, so we're going to have two parts: bullet flying and the thing at rest, them together and they're moving, and then a final point where the thing has moved. So let's only worry about right now the velocity of that thing right before it starts to move. Okay, so there's going to be a collision happening between them. So we're going to have the mass, let's call it little m. That's the bullet's mass. Little m represents the bullet's mass, and v1 will represent the velocity of the bullet. That's going to be then finally equal to the sum, right? The whole thing together, because it's going to be inelastic. They're going to stick together into one thing, and they're going to travel at some velocity v2. Okay, so from a momentum point of view, that's all that happens. Okay, and I can then isolate. So v1 is going to be equal to m plus big M all over little m, all multiplied by 2. And then if I can break this up, if I factor this out a little bit here, not factor, sorry, if I break this up into a sum of fractions with the lowest common denominator, this can be also expressed as m over m plus big M over little m, 2. Okay, and little m over little m as 1. So we have a final expression that the velocity of the bullet is going to be equal to 1 plus the ratio of masses, big M over little m. Okay, there's our first expression we can use. So let's just remember we have this expression here. That's our velocity. Okay, now let's look at some geometry quickly. Okay, so we know that, so this expression tells me what the velocity of the bullet is with respect to the final velocity of the big block, right? So for example, if let's say the mass, let's say these masses are the same, right? So let's say a big M and little m are, the bullet and the thing are the same mass, doesn't really matter. But assume they are. It will be 1 over 1, which is 2. So this whole expression will become 2. So then the initial velocity will be twice the velocity of the thing. That makes sense, right? Because when one mass hits the same mass, then we'd imagine they bounce off with equal and opposite velocities, right? So this would be half will go that way, half will go this way. This is at rest. This comes and collides into it. Well, here we are. This comes at rest, collides into it. Then half of the velocity would go one way, half the velocity would go that way. Newton's third law, right? So so this expression does make sense. We're going to have a much larger big M. What's that going to do? How's that going to affect things? That big larger M, is that going to make V2 really big or V2 really small? Think about that. Okay, so now let's do a little quick geometry here. So we know that the pendulum, ew, that's ugly. We know that there's the pendulum and it's a length L. Okay? It's going to swing up at some angle, we're going to call it alpha, right here. And so here's my little thing. And we know that it's going to swing up from there to there. That's what our thing is doing. So we know we can calculate this height difference here, this h, right there, right? So I know that this is L. So I can, looking at this, if I make a little triangle here, make a little triangle there, then the cosine of my angle, alpha, is going to be equal to the adjacent, which is L minus h, right? This piece here. If this whole thing is L, then this little guy is L minus h divided by the hypotenuse, which is just L, right? So then rearranging things here, I can multiply both sides by L, cosine alpha, L minus h, and then I can keep going. Oh, whoopsies. Then I can keep going, and what's the h? If I bring h over, h is going to be equal to L minus L cos alpha. I can factor out my L. I get 1 minus cosine alpha. Right, so there's another expression. H is equal to L 1 minus cosine alpha. So that's what we see here, right? We have that 1 minus cosine alpha, that's what we want. So we're getting there, we're getting somewhere, right? So I have an expression here for V1 as V2. And now let's go to energy considerations. Okay? So I know that the kinetic energy of the whole system, M1 plus M2, after it hits, right, is going to be equal to the potential energy once it rises from here. So I have my mass here. It's going to rise up to my new mass. This is M plus M, little m plus big M, little m plus big M, and it's going to rise up to that new height. That's going to be the potential energy at that maximum extension, or maximum angle, pardon me. That's going to be, my kinetic energy is 1/2 the mass of the bullet plus the mass of the block, V, which one's that? Which V? Is that V1 or V2? That's V2, because that's the velocity of the whole system after it hits, V2 squared. And then mgh. Okay? So now that I have all this stuff, I'm pretty much good to go. Oops, I made a mistake. Remember, it's the whole thing. So that's m plus big M gh. And nicely, things cancel. Right, so V2 is 2 times g times height square root. Right, we know that. We've seen that expression before. Now I can replace h with this guy. And I can replace V2 with this guy. All right? Oh, I got my V2 here. So I'm going to put in this expression here, my V1 expression, I'm going to replace V2 with 2gh. And so let's rewrite this here. So 1 plus m for little m multiplied by V2. What's V2? That's square root. Now let's do some fun. Let's go here. 2g. And what's h? Oh, that's L 1 minus cos alpha, right? And this whole thing is to 1/2. Is that what we wanted? Let's go back and check. Oh, look, that is exactly what we wanted. Right, just rearranged. So, therefore, the velocity of my bullet is equal to, okay, so it's going to be 2 times gravity times the length of my string, 1 minus cosine of my maximum angle, take the square root of that whole thing, and multiply by 1 plus the ratio. Okay, so there's my final expression for the velocity of a bullet that hits a ballistic pendulum. Okay. Again, apologize for being messy here. I know it's not ideal. I'm just gonna. There we go. Okay. I'm doing this on my laptop screen with this little tiny pen, and I'm doing my best. Okay. So hopefully that helps out. What's next here? Oh, nothing there. All right. So what I'd like you to do now. Okay, what have you done? We've looked at. We treated these things as inelastic. Inelastic, remember that elastic means that energy is conserved. Anytime we talk about, consider the collision to be elastic, then we can say that K1, Ki equals Kf, right? Inelastic means we've lost some energy. And if it's asking us, is it elastic? We have to check to see if the energies are the same. Like this problem, then we used momentum to calculate the other velocity. Momentum will always be conserved. Remember, the conservation of momentum idea is just an extension of Newton's third law. If momentum was not conserved, Newton's third law would be wrong. Okay? Really important that we can always conserve momentum. Momentum conservation is one of those amazing things that happens in the universe, just like energy conservation. The problem is when we have a situation like this, energy conservation doesn't necessarily work because energy can be lost to the system, right? The second law of thermodynamics messes up all that stuff. So even though we have the first law to help us to try to solve these things, the second law will always get in the way because light, sound, all this sort of messy stuff will mess with things. Okay, so I'd like you to go through these problems, 8 to 14. They should be on the website. Shortly, I will post the answers to them as well. All right, so I hope all you guys are doing awesome. I know this is a stressful time for everybody. Take her easy, and if you get bored, here's some physics. Okay, so let's do these problems. I'm gonna go right now. I'm gonna shut this off. I'm gonna go do those problems, and I'm gonna scan them, and I'll post them. All right, take care, guys.